Welcome, everybody. I was hoping that Siri would greet you tonight, but she had a big day at the Worldwide Developers Conference and then booked it right to the Warriors game, so it's just me tonight. Thank you all for joining. I'm with Wipro, a global business manager with Wipro Technologies. We serve about 900 of the Fortune 1000, everything from outsourced research and development to IT providing and consulting. So we're really happy to be supporting you, this deep learning community. And if you have any questions, feel free to say hi after the show.
So, I want to give you a little history about myself. InfiniGraph's my company. I'm here with Paul, data scientist, and Ryan, who's director of sales. And we've had 5 years in the making. So we've been basically processed over 1 billion pieces of content, 2.5 million videos, and we started developing what's called a trend score around video content. And then we cut our teeth with AppNexus, started doing native advertising. And we got very lucky, got into an opportunity with Paramount and Disney doing movie promotions. And one of the things that was very frustrating about video was that you could do all this advanced technology, but inside of the video container, it was relatively dumb. And I'm sure you guys have experienced video with a thumbnail being static, but here's an actual example of what we were doing, is cycling through and finding images that just resonated well. And what I'm going to be doing is talking about how we went about understanding video analysis. Someone's they're heckling. And we're doing video intelligence. And so we're going to go right into talking about that. And I'm sure everybody here has experienced like Snapchat, Instagram, Facebook. Video is hot, no doubt about it. But how do you create a thumb-stopping video? Believe it or not, that image has everything to do with a person stopping and actually playing that content. And video starts are one of the biggest money-making components of video today. It's a multi-billion-dollar industry, just video in itself. But if somebody doesn't watch the content, there lies the problem. Is that, in fact, you've got this great linear body of work, but you're stuck with one image. And if that one image is not nailing it, you're missing it. And so that's the key that we're going to talk about. We're going to talk a little bit about what we're doing with convolutional neural networks and some of the big 3 takeaways. So here everybody knows about fast data, right? Well, we deal with that every day. So hundreds of thousands of streams coming in. Third-party data, we got location-based data, we got completion, hover, social graph, viewability. All of this is coming in at once. And that's a real big challenge because we're having to monitor all this stuff virtually on a real-time basis to make adjustments to the video. And this is a really cool graph because we're really looking at not only one video, but like for one publisher, we had to process 300 videos a day. So it's a relatively undertaking. And then we're having to adjust these videos across multiple endpoints. And we'll talk more about that at the later in the discussion. But I just wanted you guys to take away the fact that we're having to deal with this video consumption. We're really reverse engineering, and we're taking content that's being on the being distributed, and there's a big deep learning challenge. And that deep learning challenge is, how do I figure out what consumers really resonate with? And it's not just the images that they're clicking on, but it's the linear body of work. And we're doing news-based content, entertainment, sports, and I've got some great sports examples which we're going to dive deep into, specifically around the Warriors. And we've been seeing lift rates with running, our product's called KRAKEN, which we'll go into obviously. But one of the things we do is we learn on actions, and that's a really incredible element, is that if I know a person's intent and I know that they're willing to play a piece of content, that's a really powerful indicator. There's also keywords, metadata that's coming from the videos, and that's very important as well, especially from when you start to predict. And there's some of the prediction algorithms that are out there that are being used, and it's all culminating around what's machine learning, how to learn and predict what you're willing to watch. We were just at Hulu, and they have it at 70%. They can predict what you're going to watch 70% of the time. That's fascinating. It blew me away. But once you start trying to predict, that's a big multiplier, because a person that commits to watching a piece of content, all of a sudden now if I can predict you're going to watch another piece and you actually execute on that, we call it double or triple. So they're actually monetizing those over and over so that individual has greater time on site. Hulu processes 1.9 billion streams a month. That's shocking. Amazon, Netflix, all of these engines here are, basically like an OTT, over the top. And one of the things that's cool about this is that, streaming media basically killed, the recording. And so now KRAKEN. Hope I'm not going too fast here, guys. But so what is KRAKEN? So KRAKEN is a video machine learning technology. One of our big focuses and this is the great example, is you've got a
little push
linear
shot,
body of work.
home.
3-minute clip has 5,400 frames. And so which one of these frames is going to make people willing to commit? Believe it or not, we got almost a 45% improvement on this by running the machine learning algo. And we're going to go into detail about why and what's behind that and how it actually occurs, where we're not only able to identify those great objects or visuals in the physical linear body of work, i.e. the video, but then we were able to present that across a distributed audience and do real-time A/B testing. And our real-time A/B testing is pretty cool. We allocate 10% to the default thumbnail or the poster image that comes from the publisher. And then KRAKEN allocates 90%. And so what we're basically doing is we're looking for this cognitive response. And we're separating out the video. So you can imagine a 2-hour clip, 2-hour video, we have to time slice that. That's real difficult, but we've really been able to figure that out. So you're seeing a real cool example of what we call time slicing. And this is a video that we just watched, but now broken out into individual time slices. So each one of these segments, in fact, can be A/B test on the individual image. The problem is that you don't want to do every image because you're going to miss what we call the apex point. Every video on the planet reaches what's called an apex point, where you have velocity. So they release the content, people start playing it, sharing it, maybe it goes viral, maybe it doesn't, but it starts ramping. That slope is really important. But once it hits the apex point, it's over, it's done. It's going to decline. Sometimes it even drops off the cliff, it's amazing. But what we want to do is extend that, make it higher and higher and higher, because that's where we can make a lot more money and actually drive more efficiency. So at the end of the day, once the video is produced and released, you can't generate any more revenue with it hardly, because it's out there, it's done. So that's what the reason why we even exist, is because we're able to increase the efficiency and push up the usability or usage of the content. And so again, back to time slicing, we've come up with some really cool stuff. I'm done being able to take long form, short form, 30-minute segments, and really draw out of the best images. And so I'm not in charge of their UI. We're going to ask them to change it. But that cycling through were the top 4 images, or top apex images. And that killed it. It really did well. And this is a larger screen. I think I shot this from the iPad. But this is, again, you're taking a linear body of work and now showing 4 images. And those 4 images were definitive that the audience said were the best. And then this is really exciting, because this has told us that these objects, these visuals, resonated with a very large body of work. But it's not just one, and this is NBC Sports, a really cool example, same thing. So we're really, it's very exciting to be able to not only find those awesome images, but then what's behind the processing. So there's an equation called entropy. And entropy has been around for many years, but this is the description of it. It's from the Wikipedia. And we're actually using entropy to help us process those videos. We actually came up with some stuff proprietary for ourselves to be able to speed things up. So we were slicing and then finding the quality, which is, and I'm going to show you some graphs that Paul was responsible for making. But effectively, this is the entropy equation that's technically being used to find quality. And we want to basically take out things like blurring, nonsensical images like logos and things that are just not usable, that we don't want to show people. And to be able to do that at scale is really difficult. spent a huge amount of time, and we're still engineering ourselves to even make it better. And the image you see in the middle here is the 6 is the highest entropy. So this is actually a visual description of interesting objects. Now we want to take that obviously a step further. Where does deep learning apply into this? And this is a great example of what's called blurry quality images. And the reason why we were so emphatic about this is that we want to start out with high quality images, but we can't do thousands. We've got to do a really small set. Because again, remember, we want to catch it up on the velocity. As soon as we can figure out what to KRAKENize the fastest, that's how we can get better performance, because we don't want to take too much time. And this is a great example of KRAKEN-based images, and then those that have been dropped. You can see that really nice grouping. And we know, in fact, when we see that, we've nailed it. That's really exciting to see that. I mean, I'm a geek, so I mean, these things make me excited. So, see a nice little clustering. So, now going to the next level. Now we got all these great images.
Curry.
And we know that they nailed them. Let's do some classification. So this is a great example, and we don't have this visualization like this, so I wanted to use this. Is from Clarify. And they've come out with some really cool stuff. Matt's an amazing guy, but he has done a real-time, you upload a video, you go out to clarify.ai, try it out, upload a video or an image, and he'll literally come back and tell you what's in it. Now, these descriptions are not as useful for us, but they're very powerful, and you can see the descriptions here. This was done very fast. He probably has, compared to Google, probably one of the largest training sets that I know of. It's actually fascinating. And this is some of the stuff he's doing, where you upload an image. And so for our cases, we have tons of images that we know have resonated with an audience, verticalized audience by content. So we actually want to know what's in that image, what caused those people to have that cognitive response. And there's been some great work. And we know who the 4 great gods are in the space, but there's been some really amazing work that's happened in the last few years, specifically around synchronous SLAM. And what's fun about this technology is that it's really taking the ability to process large amounts of video objects and then identify them. And by the way, I'm going to make this available so you guys can obviously dive into. And I'm not the expert on SLAM, by the way, don't get me wrong here. But I'm very excited about what they're doing with this, because it's really being a foundation for some of the strategies that we've implemented and applied. But this is a real example of what we call a real-time analysis of video, and then being able to detect the objects. So if anyone's here has checked out Google Vision, it's just absolutely extraordinary that they opened this up. I was very grateful about TensorFlow, obviously. But this is an awesome example of just the depth and breadth of Google Vision, and it's for anyone that wants to do a large-scale image classifier at a super low cost to create a training set. This is it. I mean, I can't stress this is a paradigm shift that Google has opened up this amazing engine. And the classification that Google's doing right now is just phenomenal. I'm not going to go into detail about exactly what we're doing with it, because that would be too much information. But I can tell you that their classification and being able to create a training set is just incredible. And they're doing things, now some of this is not released, like some of the emotional components they're going to show. But this is an actual image cloud that they created, and then through the API you can then upload an image or a bulk of set of images, and it'll come back and give you this depth of classification. Now we need more classification because we want to get more robust, and that's a big challenge because it's also expensive. Has anyone here ran convolutional neural nets or quote 1, 2, 3? Yeah, so it's expensive. And they're now charging it through the cloud. There's several companies that are doing cloud-based. We don't want to process 20 million images on that. So there's a give and take. But one thing that I got really excited about this when I first saw this was this emotional. This is very important to us, is being able to then identify within the video or the image emotional elements. And they were having people are angry, sad, and that was very cool. And another thing I think that they're doing really well with, and there's a company called LogoGrab, and basically they're doing it where they're creating a whole compendium of locations, logos, sites. And this is another very important component, because if I can find out, well, what's in that video, what was that object that people resonated with, but then actually be told what it is, I can create that library. That library is really important for connecting, and this was the whole logo aspect so there's a race raging, and it's a huge race, both machine and software. And this is the old school. What you see on the left here, or right here, this has been around for decades. These guys have been around for a long time. You should check them out. But they've been doing line-based machines where emit object recognition for like Coke machines and stuff like that, large scale. But here's ours, and we had a friend of ours create this. This is a 8 GPU that we have multi-TensorFlow running, which we're pretty excited about. And this is portable. I won't go too much in detail about it, but gave us a little information leg up. And this is an actual analysis of a huge amount of images. And I just wanted to show you, like OpenCD has been around for a long time, but they're really making some touch. Who's used Torch here? Anybody use Torch? Torch, awesome. I like TensorFlow. And I'm not going to wasting my time telling you what this is, because that's you guys have probably heard 20 presentations on that. But this is one of the coolest things I saw. I was very excited when the guy at Google from TensorFlow Group talked recently, and he just showed this flow of how with the ReLU and the layering, repeating and feeding itself back. That was the first time I actually saw this. That was the best visual in the world. Because it's sort of kind of hard to imagine this if you're not a mathematician. But all of the images you see on the background here have all been grouped in class through this methodology. And at the end of the day, it's a probability. So we want to have high probabilities if we're going to do recommendation. And what's reinforced deep learning?
Yes,
well,
number of players 0.
who here has seen war games? See, this is a problem about being in the valley, young versus old. But this is when I saw this. I was a kid. I was so excited because this is the first time I saw. I can't hear anything. It's more exciting if you have actually audio.
Learn, goddammit.
Thanks. But what's actually neat is the producers here really
must be caught in the loop, storing more and more power from the rest of the system.
This is the first time, at least I saw
9 numbers.
movies where there was
Battery's got the code, it's going to launch.
reinforced learning. But in fact, this is what it was. This is brilliant to me. But this is the whole point where the nuclear weapons and one figures out, oh shoot, I can't tic-tac-toe. It's learning. Yeah, I know you guys missed that, but that's what Matthew brought.
General Purpose AI. Its
so I
name
wanted to
is
run this clip real
AlphaGo,
quick.
and it was
No, we
made by
definitely want the
Google's
audio
DeepMind
here.
division. The AlphaGo AI algorithm beat a human at the world's hardest game. This is a historic moment in computer science and artificial intelligence.
This is probably the most important event that's
Game
happened
1
in
surprised Go Master Yi Sedol.
for 33 years.
Game
I've been
2
waiting 33
left him
years.
speechless. And in Game 3 he felt
So
powerless.
Go is a real hard game. I tried
Sedol
playing
came
it
back to
when
win
I
in
was
Game
high
4, but the
school
final
and
game
college, and
ended
I
with
couldn't get
Google's
it.
AlphaGo defeating the Go Master
So I mean,
again.
I think maybe the game ended.
But
No, I don't think so, because it looks like
this is a big deal
we is still
because the
counting.
machine
No, I think he resigned.
beat a person.
Wow, I think you're right.
And they were
Wow.
predicting that we were
Wow.
This was the moment a computer called AlphaGo beat a master of the ancient Chinese game Go.
So what exactly is Google DeepMind? Where did it come from?
there's a
And what
couple
can the
things in there
company's
that are really
artificial
fascinating I
intelligence
wanted to
actually
show you
do?
guys.
In this video, we'll find
takeaways.
out. So firstly, a few questions. Why is this important, and what's all the fuss? AlphaGo shows that machines can really learn. How so? Well, instead of using brute force to calculate all the moves it could make, like previous AIs, Go used reinforcement learning and neural networks to mimic the learning process of a human brain. Keep in mind that the ancient Chinese game Go has as many more possible moves than chess as there are atoms in the entire universe. So there's no way of just calculating every possible move on the board. That's practically impossible. For this reason, Go is the holy grail of AI, and learning to do such a task from scratch.
If you ask a great Go player why they played a particular move, sometimes they'll just tell you it felt right. So the one way you can think of it is that Go is a much more intuitive game, whereas chess is a much more logic-based game.
AlphaGo's system uses deep neural networks, which approximate the web of neurons in the human brain. These networks learn to perform tasks by analyzing large amounts of digital data. The AlphaGo team took it a step farther. Using reinforcement learning, they set up countless matches in which different versions of AlphaGo played each other. So AlphaGo learns from human moves, and then it develops its own strategy. It understands how humans play,
tying it back
but it
to
can
the
also
war
look
game
beyond
stuff,
that
was really
to play an
exciting,
entirely different level of the game.
He's going to say this, and
so the way we start off training AlphaGo is by showing it 100,000 games that strong amateurs have played that we've downloaded from the internet, and we first initially get AlphaGo to mimic the human player. But of course, ultimately, we would like AlphaGo to be stronger than human amateurs and compete with the top professionals. So the way we do that is, after we take that first version that's learned to mimic human play, we then allow it to play itself 30 million times on our servers, and using reinforcement learning, the system learns to improve itself incrementally through avoiding its errors and increasing and improving its win rate against older versions of itself. And after all these games, then you end up with a new version that can beat the old version, the original version, around 80–90% of the time.
Well, because the machine learns from more experience
a lot of people
and
are talking
data,
about how
it
scary
can
AI
perform
is going
well
to be
across a wide variety of tasks,
learning.
straight out of the box.
I think
okay, so that's enough talk. Let's watch the system in action, learning how to play Breakout. And remember, the machine didn't have any foreknowledge as to what task it was going to complete. It had to figure out how to do everything only from its own experience.
So these are the games I grew up with.
The machine before training. So this is literally the first time the machine has ever seen this data stream, and it's controlling the green rocket here, and you can see it's losing its 3 lives immediately.
So this is a
so it's basically terrible at the game, as you would expect. Now, after training, this is like overnight. We leave it playing the game overnight on a normal computer, so for about 8 hours. You come back in the morning, and now it's superhuman level. So now the machine can play Space Invaders better than any human can. It's modeled the world, the game world, so well. It knows where the Space Invaders will be ahead of time. So as the Space Invaders speed up, when you get less of them on the screen, it fires the final shot as a kind of predictive shot of where the final Space Invader will be in a few seconds time.
But the cool thing is, after understanding how to play a few games, it will be able to transfer this knowledge and understanding across more games.
Or do good, right?
At the moment, DeepMind is currently playing games from the 1970s
some of the,
and 80s.
I don't know if you remember Doom, but they're actually now experimenting with
games, such as Doom,
enabling Doom.
In the early
so this
90s.
Doesn't create very much excitement for me personally
AI be used for?
to teach an AI system how to be the best shooting platform. But
things like healthcare and science,
he's obviously putting a lighter touch on it.
In those areas by helping.
Fortunately, this will be used, and it's probably already used by the military in some form.
This may seem frightening, but the reality is,
the reason why I'm excited about it is because these are some of the problems that we're trying to solve ourselves.
As we humans
which
work with
is
these machines,
to
our genius will
take
only grow in tandem
massive
with our
human interaction on images and distill that down, and then really next thing is to create a very robust prediction
and machine
and identification system. And that's really our big next step as a company so what's next for us? Just a quick recap of where we've been and what we're doing. You can see here is called the video graph, and again we're processing a huge amount of videos, identifying those images, and then we identify the individual sets. The objects itself is very important to us. Being able to run a robust classifier that can be used for a whole process of next level is called prediction. And then here is a great example of the slicing aspect I was talking about. So being able to then identify very quickly which regions, which sets are performing well to the distribution points. And this is a real example of what we did for Interstellar. But these are all these images and videos here are the ones that were distributed. So you can imagine just the wealth of information and the possibilities. We're just scratching the surface, which is exciting. But this is an exact example of the distribution over different publishers and different networks. And that's it. Thank you. So Paul's better answering anything around entropy, but I'm more than open to ask any questions, or you guys can ask questions, please. I'd love to have a conversation or know more about what you guys are working on. It'd be awesome.
Okay, so I'll wander around and pass out mics, so folks can ask questions.
Great talk, very fast. Thank you. Although it was at some point a little hard to understand both of you, but it was still very interesting.
Thank you.
The audio guy for that.
New style of presentation, not slides, but you being paced by the machine, which is actually interesting given what you're talking about. So one thing, predict 70% of the time what the next video is that people watch, which to me brings into question what free will is. But actually, do you think you can do that much better with your techniques? Can you get to 90%? Determinism in human behavior as far as video clicks go, and is that geographically the same across the world, or do you have?
No, it's definitely depending upon the culture, the visuals, the content. We've already proven just with KRAKEN alone that different visuals distributing to different regions perform differently. So that was cool. We believe things, but we're very data-centric companies, so we like to see that. How far can we go with prediction down to the individual level? We're tapping into a new field of cognitive science. If I present to you 1 million images and you display behavior on those 1 million images, and I've now created a graph of your behavior on those visuals and then process those visuals into a graph itself, then yeah, I'm going to get pretty damn close to predicting what you're going to, just by picking a raw image and say, you know what, those contain all the elements that are going to hit your neurons. So yeah, I think we're going to get there.
Hi. I had a quick question about how you are doing the actual, I think you call them actions, detecting actions. Or,
yeah.
So it's very clear how you would analyze still images or even individual frames using CNNs. But are you using RNNs for the actual? No, you're not. What are you using? Generally.
I prefer not to talk about anything about that specifically. I mean, in the presentation, it, I think, went to the depth that was required. I mean, I can get with you offline.
Sure.
Yeah. But to answer your question about measurement, the first point of measurement is the clicks, the play. The location's really important. The device type.
Okay.
So there's all those elements. There's a referral URL, because we see all the referral URLs going in.
Okay.
So yes.
When you ask a question, to introduce yourself and mention where you're from.
My name is Ramakrishna.
Hi.
And I'm coming from HP. I don't do much of machine learning, but I'm curious about this hardware device that you have here. You're using TensorFlow?
Yes, it's running across all 8 GPUs, yes.
Yeah, so Google came up with the TensorFlow chip a while back.
What'd you say?
The hardware chip, GPU.
Who came up with it?
Google TensorFlow.
Oh, yeah, well, I showed that image and I didn't get a chance because I was being outpaced by the machine, but those were all, like NVIDIA. Google has their new design, which no one really knows what it is, but
okay, sure.
Yeah. So are you asking me?
Yes.
I don't have that chip. I'd like to have that chip. Yeah, it would be great. They're not selling that chip.
Yeah.
No, those are just NVIDIA processors.
Hey, my name is Somnath. I'm from Walmart Labs.
One thing I read about in TechCrunch, there's a tensor processing unit. I don't know whether you're talking about that. So, okay. So my question is like, the way I understood is like you replace the thumbnail with set of selected images which you think the best and you're going to get the best response. But I see there's one dimension inherent to it, like one static image versus you are rotating few images. So that is inherently going to improve that. So let's
actually, if you have bad rotating images or the sequences are not right, it's actually a negative effect. Because just rotating may get someone's attention, but the problem is that if it's causing the brain to say, hey, you're turning me off, you're not turning me on. And we actually can monitor which image they are willing to click on. But we don't do that, we only do that at the end. So through the process of A/B testing, we're only doing A/B being one against another. So we're not rotating during the visual processing because then that would mess up the potential results. We want to find the best sets of images.
I see.
So the rotation only gets kicked in if KRAKEN says rotate or not. So it'll make a choice, or it'll go 1, 2, 3. We don't go past 4 because the curve on the fourth one sometimes is low, so it may get kicked out. So it's doing that on the fly. We don't really know what's happening. It's just happening. Again, KRAKEN's it's a girl to us, but she's just trying to reach the highest apex point and hold that apex point as long as possible on a per video basis.
So even with the single image, you are seeing the lift?
Yes. Oh, absolutely. Yeah, because we're killing it. We go through and it's going to find that awesome image for that distribution point, because it may be 4, 5, 10 different points where it's being distributed, and those may change. And most times they do. Sometimes it's a very small variance, and sometimes a drastic variance.
Cool.
But yeah.
So
That's your
how
question?
integration work? Is it like you solve a GIF image?
No. There's multiple images being created because of the scaling.
Okay.
And so when we ingest the video and process it, we're creating a whole set of images. And then once those get processed down, then those are being used distributively. So it could be, I think it's PNG, GIF, JPEG. We don't do anything with GIF. As a matter of fact, I'm 100% sure it's no GIF.
Okay, but the publisher tag, if you're just having a thumbnail image, how will you rotate that? You need to have GIF.
Okay, yes. So we're actually integrated with the top 4 video platforms. So like JW Player, Uala, Bright Cove, Video.js. God, what's the other one?
Got it, makes sense.
The platform is another one. So all of those have APIs, or they allow you to create what's called a plugin. So we live inside the player. And by living inside the player, once the player gets distributed where it is through the video CMS, we're there sitting there doing our thing at what's called the DOM layer. So.
Cool. That's nice. Thank you.
How many events do you expect it to take before it typically converges?
God, that's a great question.
Or is it even constant?
No. It's a brilliant question, and it varies.
Do you have an idea of the variance?
I'd have to sit down with Chris and ask him. This is. If you give me your well, no, it could be like 20 to 40 on the event side, because it depends upon it depends upon how many distributions, how many locations, devices. I mean, those are coming in, and then there's the actual clicks itself, and then all of the images that were typically will get down to maybe 100 to 150. We're trying to get down to smaller. That's where the prediction comes. It says when we process a video, we're saying, I would prefer that we don't do any A/B testing. We would just say, here are the images. We know they're going to perform well, so we start off at that very second, because some of the sites we're on are doing millions and millions of plays very fast. So every minute, every second we leave on the table, we're leaving a lot of money on the table that we could have optimized. So we have to. So I think that answered your question.
Thank you.
Question over here, but yeah, black t-shirt dude, what's your name and where are you from? That's you, Chris.
Oh. My name is Chris. I'm from a company called AI.
Okay, we have a question over here.
Hi there. My name is Matt Su. I'm an independent consultant. My question is, have you noticed any evidence of, or do you think there's any danger of you sort of training the people to be trained by the images you're excited by and somehow normalizing on some smaller set of uninteresting things that you can now always predict?
You know, that's a conversation we do have, and we're concerned about. You know, it's like if we over-present mundane things, could we just be measuring a mundane event? You know, we witnessed that actually in some like surveillance videos where it was real grainy, really wasn't a lot changing. I mean, it was some movement, but it was very difficult. There's a lot of other videos that are like we're running on a company right now that has dog videos, and you know, the dog is running in a circle, you know, and it's, you know, so we don't perform really well because it's, you know, do you like the tail end of the dog or the front end of the dog? You know, I mean, it's, so I mean, those are some problematic types of content that, you know, will we get a good piece out? And so, but this is a conversation, a real conversation we actually do have. For the majority of the mass majority of the content, that doesn't apply because it's a really good linear body of work. There's great transitions. It's crisp. It's HD because we ingested HD. So in that case, we kill it every time.
Is that enough, or will people just start liking some small set of things?
Well, yeah. So this is a great point. So we've had talking head. We call it the talking head video, where the guy is just in front, a green screen behind him, and he's just sitting there talking. But believe it or not, humans will resonate on the facial expressions and the eye movements, and so we're actually seeing that happening. Because we're sampling out so fast over a large set that we can quickly find out which facial expression or which eye movement or just the head position applied or resonated really well. And it's quite uncanny. I mean, you know, somebody looking down, if they're looking at a book, that could be interesting, or they're pointing, that means that they're, whereas if they're looking at you head on and just if they smile, that actually induces a positive response. So there is some correlation there, and that's the reason why we want to obviously process the images, because we want to be able to detect that physically and then zero in on that.
Chase, my name is Nishank and I'm a graduate student at San Jose State University. My question is that the input to the KRAKEN is just the video to analyze and also sample data, like, you know, this is the data images to which user resonate.
Yeah, so we actually, so one of the gentlemen here was asking a pretty detailed question. So we actually have a historic on performance, and we're using that historics to help us do better selection. And so for every time we can run on a body of work or more bodies of work that are similar and create it, that's we consider as a training set, because we are now selecting smarter and faster and better images quicker. And I don't know if I'm answering your question, but I answered the gentleman's question, which was about the measurement being clicks, views, and then the location of other components that are coming in. You can ask your question again if I don't feel I've answered it sufficiently.
Can you tell one use case scenario of using this KRAKEN, how it can be used?
Yes. So the whole presentation had a huge amount of use cases, but I will do that. Any publisher, broadcaster, NBC, CNN, anybody and everybody, if they're, you know, if you're hitting and looking and watching videos, that's the use case. So it's humans interacting with video content. That is the use case. So I hope that answers your question. Is that too broad?
If there is an NBA video, you have a free data with you processed data.
Yes.
These are the images to which user will resonate.
Well, we start out with a set that we have a big belief in that is going to work well. And we still put them out in the audience because at the end of the day, we believe that the audience, that's that whole reinforced deep learning for us, because we're using the audience to reinforce our previous knowledge to get better and better and better. And we've seen that with our improvements in our lift rates.
Thank you, Chase.
Yeah, sure.
Thank you.
All right. Well, thank you, Chase. Let's thank our speaker one more time.